Hi, my name is João Loula, and today I'm going to talk about joint work with Kelsey Allen and Josh Tenenbaum on combining rules and simulation to explain infant physical learning. So to start out, take a look at these scenes. You can quickly judge whether this green block is going to fall or not, or whether this blue box is going to fit inside the yellow container that's lowered onto it. The ability to make judgments like these develops gradually over a baby's first year of life. So in the case of support, by around 3 months of age, infants expect an object will remain stable if it's released in contact with the platform and to fall otherwise. By around 5 months of age, they expect the object to remain stable if it's released above the platform, but not if it's released beside it. By around 6.5 months of age, infants expect that the object will remain stable if a large amount of its bottom surface is on top of the platform, but to fall if only a small amount is. And finally, by around 12.5 months of age, infants expect that the object will remain stable only if most of its volume is above the platform. In the case of covering, at around 12 months of age, infants will expect that relative height plays a role on whether an object can be lowered onto another one. Now, we know that babies can be taught some of these concepts from just a few examples. So Wang and Baerjian find that 9-month-olds will learn about relative height as an important feature for covering events after being shown just 3 pairs of examples. And Baerjian and de Jong showed that 11 and 12-month-olds can learn the rules of support for an asymmetrical object from just 2 or 3 pairs of examples. Now, what's very interesting is that infants seem to have strong constraints on the kinds of rules that they're capable of learning. So it turns out that 11 and 12-month-olds won't learn from these asymmetrical object examples if you show them non-physical data where a block falls when most of its volume is on top of the platform and vice versa. And likewise, 9-month-olds will learn about relative height as an important feature for covering events, but not if the covering object is shown to have a false stop that would have rendered the observed events physically impossible. So what accounts for this? Well, currently the main model for these phenomena is explanation-based learning. In explanation-based learning, core physical knowledge is represented by logical propositions, and when the learner sees a surprising event, she forms an explanation that needs to be logically consistent with these core knowledge propositions. So, for instance, when given some data about when asymmetrical objects fall or not, infants can construct a rule that says that an object falls if most of its volume is unsupported, but when shown non-physical examples, they can find a rule that doesn't violate their core knowledge propositions, like an object behaves as a unit and larger effects overwhelm smaller ones. Now, the idea that infants create explanations that need to be consistent with their core physical knowledge is a very elegant way of accounting for these surprising results. But one of the difficulties is that this relies on this propositional description of core physical knowledge. Now, this might be enough for the simple examples that we just discussed, but eventually we would want to expand this model to account for things like collisions or fluid dynamics, and it's not entirely clear that we'd be able to get there by positing a very large propositional knowledge base. So, what's the alternative? Well, recent work has explored the possibility that infants have an approximate model of physics that they can use to imagine how scenes will unfold. Now, these simulation models have complementary strengths to rule-based accounts, like explanation-based learning. As a model of domain general and core physical knowledge, simulation is a very powerful and a very flexible model, and rules extend simulation very nicely in tasks like few-shot learning, which require more logic-like reasoning. So, in this work, we hypothesize that rules and simulation in conjunction can explain the successes and the constraints on infants' few-shot learning of physical events, whereas just rules cannot. And we test that hypothesis in 2 experiments on support and covering that are inspired by the developmental work that we discussed earlier. Okay, so here's an overview of our model. It takes as input a handful of scenes, along with binary outcome labels like whether a block has fallen or not. And from that, it infers a posterior over programs that classify those scenes. And crucially, this inference procedure operates over an augmented data set that includes noisy simulations with different initial conditions. And these thought experiments, in practice, constrain the space of learned rules to be consistent with the agent's background knowledge. So to start, let's talk about the data. Now, as we said, the data consists of binary outcomes as well as the initial states of the scene. And the state is a full-blown physics engine state. It includes the object's positions, their velocities, their shapes, and their dynamic parameters. Now, the way our model interacts with the state is by generating programs that run on the state and try to classify the event's outcome. So let's unpack this now. So the goal of the program induction module is to take in these examples and learn a rule, which is a program that, when run on these states, correctly classifies their outcomes. Now, the way that we'll search through the space of all possible programs is by doing Bayesian inference. We'll try to find programs that strike a balance between how complex they are and how well they classify the data. So if you see an example of a block on top of a platform that stays supported and a block outside the platform that falls, you might posit this program, which says that so long as the block is in contact with the platform, it doesn't fall. It's a very simple program that explains all of your observations. Now, if you introduce this additional example, where the block is in lateral contact with the platform, now the simplest program that correctly classifies the data might look something like this, saying that the block stays supported so long as the contact vector that goes from the block to the platform has the same direction as gravity. So the way we define both the space of possible programs and our prior over them is through a probabilistic grammar. As you can see, it contains concepts like checking whether two objects are in contact or comparing two objects' attributes in the scene. Now, many of the specific choices of primitives that we made here could have been very different, but for our purposes it will suffice that this is a small language that can express the kinds of physical concepts that we've been discussing. So we take this prior over programs and we combine it with a likelihood function that's essentially binary, plus or minus a very small slack, and that gives us our posterior. Now, in practice, this is a very difficult posterior to approximate over a potentially infinite space of programs, and we do it by using a recent technique from Silver, Allen, and colleagues, which I'm happy to talk more about during questions. So we'll test the simulation augmented model as well as the pure rules model in two experiments. One experiment in support few-shot learning, inspired by Bayer-João and de Jong, and one experiment in covering few-shot learning, inspired by Wang and Bayer-João. And what we'll do is we'll train and test these models with examples similar to the ones in these studies, and we'll measure the model's surprisal by marginalizing predictions across the posterior over rules. Then we can qualitatively compare to the results in these studies. So let's talk about the support experiment. So we use the following 5 training examples. One where the block is entirely above the platform, one where the block is entirely outside the platform, one where the block touches the platform but only laterally, one where the block is mostly on top of the platform, and one where the block is mostly out of the platform. Now, it's important to note that these examples depart from the ones in the Bayer-João and de Jong study in a few important ways. The first is that even though we want to test the concept of amount of contact, which relates to the last 2 examples, we include these first 3 training examples as well. And we do that because our model doesn't start with a rough rule that it refines, just like infants do, but rather it starts with no rules at all. So these extra examples are there as a stand-in for prior knowledge that infants are bringing into the task. Now the second departure is that we are testing examples of an amount of contact rule, which is learned by infants at around 6.5 months of age. Whereas the Bayer-João and de Jong paper tests a proportional rule using asymmetrical objects. So we made this choice because it allows us to work entirely with bounding boxes and their properties. So that made things a little bit simpler, and future work will look into extending this to asymmetrical objects. So following Bayer-João and de Jong, we'll have 2 training regimes, one with physically plausible outcomes and a non-physical one, where the block that's mostly supported falls and the block that's mostly unsupported doesn't fall. The simulation augmented model will sample 5 additional training examples by placing the block randomly along the length of the platform. And then both models are tested on 2 displays, the expected one, where a block that's mostly supported does not fall, and an unexpected one, where a block that's mostly unsupported does not fall either. Okay, on to the results for this support experiment. So, in the condition with physical training data, both the pure rules model and the simulation augmented model learn an adequate posterior over rules. And so they both end up finding the unexpected test events more surprising than the expected ones. Now, when presented with non-physical training data, the models differ in their predictions. The pure rules model happily accepts that objects with most of their base supported will fall, whereas those with most of their base unsupported will not fall, and it learns a program classifier according to that. So what happens is that it becomes surprised at the physically plausible outcomes and unsurprised at the physically implausible ones. Now the simulation augmented model, on the other hand, generates additional examples using its simulator that contradict the non-physical examples that were in the training data. Therefore, it has trouble learning a program that accounts for the data, and as a result, it's moderately surprised by both kinds of test examples. The results in Baillargeon and de Jong, though relating to asymmetrical objects, are qualitatively similar to the behavior of the simulator augmented model here, where 12 methods learn a mass distribution rule from two pairs of physically plausible examples, but if non-physical outcomes are shown instead, infants show no difference in looking time across the test cases. Here we show the maximum a posteriori program that the model found in the support experiment. It checks whether the vector that goes from the block center to the closest point in the platform is parallel to the gravity vector. Okay, so now for the covering experiment. Here we use 3 training examples. In the first one, a cover is successfully lowered over a box. In the second one, a cover fails to cover a box that is wider than it. And in the third one, a cover fails to cover a box that is taller than it. So again, we're using a broader range of examples than in the original developmental experiment. Here, the example with the wide box is meant to teach our model that relative width is also an important variable, and it's not present in the Wang and Baillargeon study. So again, following Wang and Baillargeon, we'll have 2 training regimes, one with physically plausible outcomes, and a non-physical one, where now the scenes unfold in the same way, but the cover has a false top that makes it so that the box can never fit inside it. The simulation augmented model samples 5 additional training examples, and it does so by varying the box and the cover's width and height. Now, crucially, when the observed cover has a false top, the model simulates a cover that also has a false top. And then finally, both models are tested on 2 displays, the expected one, where a tall cover covers a tall box, and the unexpected one, where a short cover covers a tall box. So, in the condition with physical training data, again, both models find the unexpected test events more surprising than the expected ones. But like before, the model predictions differ in the non-physical training condition. Here, the pure rules model learns a rule about the relative heights of the cover and the box and makes the same predictions, disregarding the physical implausibility that comes from the fact that the cover had a false top. The simulation augmented model, on the other hand, after running simulations with the false top and seeing it was impossible for the box to be covered, cannot find any plausible rule, and like in the support case, defaults to having no strong expectations over the event outcomes. Now, this is in accord with the results in Wang and Baillargeon, which showed that 9-month-olds will learn a relative height rule from a pair of contrasting examples, and therefore look longer when a small cover covers a tall object than when a tall cover covers a tall object. But if in the teaching trials the tall cover is shown to have a false top, infants look the same at both test displays. Here we show the maximum a posteriori program that the model found in the covering experiment. It just checks whether the box's width and length are smaller than the covers. Okay, so to summarize, we show that in contrast to just rules, a combination of rules and simulation explains what infants learn and don't learn in few-shot physical events. Now, there's a couple of outstanding questions. First, if you can learn from doing thought experiments with your simulator, then why do you need the data at all? Like, why can't you just do zero-shot learning? And we speculate that the data might be important for deciding which thought experiments you should run. So, for instance, you can exercise counterfactuals like, what would have happened if this block were a little bit to the left, or if it were a little bigger? And in future work, we want to look into this hypothesis by having some automatic ways to propose informative simulations to be run, given some observed data. Now, a related question is, if your simulator is already pretty good at prediction to begin with, then why don't infants just solve the task correctly the first time they're given these tasks? And one possibility is that when you run your simulator, you need to decide which aspects of the scene and of the objects are important and need to be included in the simulation. So it might be that upon your first encounter with certain situations, you make simplifications in positions or in object shapes that give you the wrong simulation outcome. And then what's interesting is that the learned rules themselves can kind of serve as a guide for the simulator into what aspects of the scene are important and should be included in this simulation. So this is something we want to explore into future work too.